Signal processing, averaging, techniques to enhance signals by reducing noise. Purpose and concept of averaging. Averaging in vibration signal processing is a technique used to stabilize spectral data and improve its reliability by reducing the influence of random noise. When vibration signals are captured, they often contain both consistent components, such as forcing frequencies from machine elements, and random variations caused by environmental factors or transient disturbances. These random variations can obscure the true vibration signature, making diagnosis difficult. Averaging works by combining multiple measurements of the same signal, which allows the consistent components to remain prominent while random noise tends to cancel out. This process improves the signal-to-noise ratio, making peaks in the spectrum clearer and more representative of actual machine conditions. In practice, averaging is essential for repeatability and accuracy in FFT-based analysis, especially when diagnosing subtle faults like bearing defects or gear wear. Without averaging, analysts risk misinterpreting transient spikes or noise as genuine fault indicators. The averaging is not just a convenience but a critical step in ensuring that vibration analysis delivers actionable insights rather than misleading data. Mechanism and benefits of noise reduction. Noise reduction through averaging is based on the principle that true vibration signals are consistent over time, whereas noise is random and unpredictable. When multiple spectra are averaged, the random noise components vary in amplitude and phase across measurements, causing them to diminish when combined. Conversely, consistent vibration frequencies such as 1x shaft speed or gear mesh frequency remain aligned and thus become more pronounced in the averaged spectrum. This selective enhancement improves diagnostic clarity by highlighting real fault signatures while suppressing irrelevant fluctuations. The averaging can be performed using different methods, such as linear averaging, which averages amplitude values directly, and RMS averaging, which focuses on energy-based measurements. Both methods aim to improve the signal-to-noise ratio, but their application depends on the analysis goals. For example, RMS averaging is useful when monitoring overall energy trends, while linear averaging is preferred for identifying discrete frequency peaks. By reducing noise, averaging ensures that analysts can confidently interpret spectra without being misled by transient anomalies or electrical interference. Concept and advantages of overlap averaging. Overlap averaging is an advanced technique designed to increase the efficiency of data collection and improve measurement stability. In standard averaging, each time block of data is collected independently, which can be time-consuming when high resolution or long sample times are required. Overlap averaging addresses this by allowing consecutive time blocks to share a portion of their data. For example, if two blocks overlap by 50%, the second block begins halfway through the first block's duration. This approach enables more averages to be computed in less time, reducing the total measurement duration without sacrificing accuracy. The CAT2 manual highlights that overlap averaging is particularly beneficial when dealing with machines that exhibit slight speed variations or when environmental conditions introduce transient disturbances. By overlapping data segments, analysts can smooth out these variations and obtain a more stable spectrum. Additionally, overlap averaging helps maintain trend consistency, which is critical for predictive maintenance programs. It ensures that diagnostic decisions are based on robust, repeatable data rather than isolated anomalies. Importance of averaging in vibration analysis. Averaging is a cornerstone of reliable vibration analysis because it enhances data quality and diagnostic confidence. Without averaging, spectra can be dominated by random noise, making it difficult to distinguish between genuine fault indicators and spurious signals. The analysts should configure their data collectors to apply appropriate averaging techniques based on machine type, operating conditions, and analysis objectives. For instance, linear averaging is ideal for identifying discrete peaks, while RMS averaging is suited for monitoring overall energy levels. Overlap averaging should be considered when time constraints or machine variability pose challenges to standard averaging. Ultimately, averaging ensures that vibration analysis provides actionable insights, enabling maintenance teams to detect faults early and prevent costly failures. By reducing noise and improving repeatability, averaging transforms raw vibration data into a reliable diagnostic tool, reinforcing its role as an essential practice in predictive maintenance strategies.